The electron configuration of an atom shows how the electrons are distributed amongst the atomic orbitals in the atom. And we can use the periodic table to help guide us to determine which orbitals will be filled next. So for instance, if an atom has an atomic number of 6, like carbon, okay, that means in a neutral atom it will have 6 protons and 6 electrons. To write the ground state electron configuration, we start with the 1s orbital and continue to place electrons into orbitals as they increase in energy. So the first 2 electrons would go into the 1s orbital. So you'd write 1s2 for the first orbital being filled. Next, you move on to fill the 2s2 orbital, or the 2s orbitals, and that orbital will have 2 electrons. So since there are 6 electrons that need to be put into orbitals, we already have accounted for 4, but the last 2 will go into the p orbitals. Now the p orbitals are a little bit different because they have 3 different orbitals for one subshell. So you would simply write 2p2 to show that you have 2 electrons placed into this p subshell. We can also use a ground state orbital diagram to give us more information as to how each electron is placed, and by that we use boxes for each orbital. So for the 1s2 orbital we have 1 box, the 2s2 orbital will have 1 box, but the p subshell, remember, has 3 orbitals, so we have 1, 2, 3 boxes to represent the p subshell. So you place 2 electrons in the 1s2 orbital first, then you move up in energy to go to the 2s2, the 2s orbital. And now, once you've done that, then see here, you come over to this graph, and then once you're done with 2s, you come up to 2p. So then we start to fill in our 2p orbitals here. So if I have 2 electrons, I want to put 1 right here and 1 in the next box, because remember, we don't pair up electrons until all of the electrons in that subshell are in each orbital are filled. And note here, I have accounted for all 6 electrons. So we have the 1, 2, 3, 4, 5, 6 electrons. Now let's go to our next example where we're going to increase the number of electrons just by a little bit. Our oxygen atom has a Z of 8, so that means that it has 8 protons, and in a neutral oxygen atom has 8 electrons. Okay, so we're working with 8 electrons here. Now if we start with the orbital diagram, we have our 1s2 box, 2s2, and then we're going to draw our p orbitals as well. So this will be our 2p orbitals. All right, so let's fill in the s orbitals first. So we have 1, 2, 3, 4. So now we're going to distribute amongst the p orbitals. So we have 1, 2, 3. Okay, now that equals 1, 2, 3, 4, 5, 6, 7 electrons total. So our next electron will actually be the opposite spin, but now we can pair up. So our final count in our p subshell will be 4. Okay, so our electron configuration comes out to 1s2, 2s2, 2p4. Now once we get to a higher number of electrons, we have a shorthand notation that we can use to demonstrate what the electron configuration is, and this is called the noble gas configuration. That is to say that we can use the noble gas configuration that precedes the element that we're talking about, and that can be used as almost a placeholder for that whole electron configuration. For instance, let's get to what arsenic an arsenic electron configuration. So arsenic's Z number is 33. Okay, the atomic number is 33, which means that in a neutral arsenic there's 33 electrons. All right, so if we take arsenic and if we kind of go backwards, if you will, along the periodic table, we actually get to argon as the first noble gas that we come to, which is a Z18. So the electron configuration of argon is 1s2, 2s2, 2p6, 3s2, 3p6. Let's make sure those add up there. Argon has 18 electrons. So you have 2, 4, 10, and 12 plus 6 is 18. Okay, perfect. So this is the electron configuration for argon. So instead of rewriting all of this and apply it to arsenic, what we can do is just write in square brackets argon and then continue from argon to get to our arsenic. So then we come out to, so if we stop at 3p6, then our next subshell that we'll fill will be 4s2, 3d10, 4p3. Okay, now let's make sure all of those add up. So we would take the 18 from our argon, right? And this would be in these square brackets. 1920, 30 from this 10 right here going into the D subshells, and then 33. Sure enough, arsenic had 33 electrons that we needed to account for. Now I also wanted to point something out. Notice here, this is the first example I did where I went into a D subshell. Now notice it went to 4s first and then filled the 3d. Even though the principal quantum number is lower than in the 4s, it's actually energetically more favorable to fill your S subshell first before you fill the D. And then that's why I have this over here. This is an easy way to remember which orbital is going to be filled next. So notice I have the 2p, then fills the 3s, then fills the 3p, then we fill the 4s first before we come back to the 3d and fill in the 3d subshells. And then notice once I put all 10 electrons into the 3d subshell, I moved on to the p again, back to 4p for the principal quantum number, the 4, and then if I were to keep on keeping on, then I would just continue on to the 5s orbital for a different element with more electrons.